See your mobile phone.
Okay, so today we summarize our knowledge of what we have learned on local magnetism, and today we will do last lecture magnetism. Several people asked me whether we are going to deal with magnetism until the end of the course, since you are a bit tired of magnetism. But I tell you about my plans right away. So as I said, today we discuss the last few important things related to behavior of local magnetism, and next week we start discuss strongly correlated systems. So we'll spend excuse me, 3 lectures on strongly correlated systems. Namely, we discuss Conde effect, namely magnetic impurities in non-magnetic metals. Conde effect plays an important role in many body physics. Second, we discuss Friedel estimations when you have a charge impurities in the electron gas. And third, we discuss strongly correlated Hamiltonians like Anderson model and Hubbard model, and see some simple model of existing charging spin density waves in system characterized by strong Coulomb interaction. So this will be 3 lectures before Easter, and this is what we are going to do. The week after the next, there will be 3 more lectures. You remember we discussed 2 options, and now for me it's clear that we cannot support doing diagrammatics because there are several ingredients missing in your education. So therefore, 3 last lectures will be devoted to behavior of Coulomb system, plasmons, and the electric constant of electron gas with a Coulomb interaction, then disordered system, scattering of impurities, and effects of weak and strong localization. And the last lecture will probably be devoted to nanosystems. I just explained you with transparencies what are the quantum dot and how the effects, how many body physics develops itself in the transfer to nanostructures. So this will be end of the course. I'm still undecided. In principle, we can have 1 more lecture after exam, because there is something I would like to show you and not included into exam. Namely, something related to very recent progress in research and modern and interesting topic, such as, for example, Latinger liquid, so quasi-one-dimensional systems, which has application in organic molecules, in physics of organic molecules, also molecular transistor, namely molecular electronics, but this still has to be discussed with Patrizia, but I would appreciate your response whether you like idea to have extra lecture after exam or you don't.
Yes, we like. Can you have some more lecture instead of one?
It's very difficult. I like your answer, and I'm grateful for your answer. Let's see. I have 3 lectures prepared for Vietnam activity last year, which I think will be the basis of a new course on quantum transport through system with restricted geometry. So maybe there is a room for 2 lectures. I will see, and of course I will give you printout of the materials. And I'm still arranging for tutorials during my absence because I'm going to Cameroon in the middle of April, and I will spend there 2 weeks and come just before your exam. But my assistant will be here, and you will have a pleasure to discuss with us these aspects of the course. I'm coming back on 24th, and we will have one informal meeting just before exam in order to ask you all questions and clarify something which you less understand and discuss. Okay. Then let's do it that way, and then in total it will be something like 20 lectures. But green functions, which I mentioned, at least 2 examples of them will be included in tutorials. Namely, today we touched a little bit upon the dynamical response functions. Namely, when we discuss magnetism, we actually move from simple things to more complex and so on and so forth. So we started with a spin subject to external magnetic field, and we have found the susceptibility, which is first of all static, and second uniform, namely this is a response of uniform magnetic field. So this was a Curie law. Then we included interaction between spins, and we obtained Curie-Weiss law, discovering that susceptibility of ferromagnets diverges at some critical temperature. But then we did another step, included non-uniform part of magnetic field, and found 2 dependence. Namely, we found the susceptibility which depends on Q. And today I would like qualitatively make another step and include time-dependent effects. And show you how the susceptibility as a function of frequency or time looks like. But what we discussed with Dinesh would be a more rigorous way to solve the equation which I'm going to derive for you today with the green functions, because what we will get today is a differential equation, unfortunately nonlinear one, which we then linearize, arrive at a linear differential equation and solve it with some simple method, but there is a powerful tool to solve linear differential equations, which is a measure of green function, so Dinesh will explain how to do it that way. And another application of green functions, which you in principle should know, is using green function method in order to solve Schrödinger equation in the scattering theory. Schrödinger equation is linear equation, so the green function method works nicely. So this example also be given to you, and we will see how the green function is a function of momentum and omega looks like. I'm saying green function, response function. So today I will rely on the fact that in principle green functions in retarded sector, namely which takes into account proper causality and response function are basically the same. And in principle, the main part of our focus in many-body physics is actually directed on the calculation of response functions. Therefore, well, when you will mature as physicists, sooner or later you will come to understanding of what we try to discuss during this course on a different language, and then I hope you will see the parallels between what I'm trying to present to you and actually more solid and rigorous theory of response functions based on the green function for many-body physics formally. Okay, so today, as I said, we discuss finish discussion of magnons in ferro and antiferromagnets, including thermodynamics, Bloch equation, Bloch law, and then we proceed with the so-called Bloch equation and the Dalton's equation, which takes into account time-dependent effects, so dynamics of spin subject to time-dependent external magnetism. Okay, were there any questions regarding the two previous lectures? Let me summarize the result of our calculations. So we have ferro and antiferromagnet. For ferromagnets, we calculated the phase diagram, I would say. The function of T. So, first of all, we have found that there is a critical temperature, and studying susceptibility above critical temperature, we have found that susceptibility diverges as 1 over T minus Tc, where Tc is Curie temperature, which we identified in terms of simple connection of this temperature and exchange integral describing the interaction between nearest neighbors, nearest neighboring spins. So this is ferromagnet. So analyzing the region below, we have found that susceptibility diverges as inverse square of the correlation length, which is the same as 1 over T minus Tc over Tc. Then, analyzing behavior of magnetization of the system at sufficiently low compared to Curie temperature temperatures, we found the ground state energy and also the spectrum of magnet. So the spectrum epsilon p was equal to 1 minus phi p, where phi is defined as a structural factor 1 over z, sum over rho, e to the power I t rho. So expanding the small p or q, doesn't matter how I denote wave vector, we have found that for small momenta the spectrum behaves quadratically. Yeah. So the bosons, the magnons, then are bosons And let's ask a question, what's the contribution, what is the behavior of magnetization at this part of the phase diagram? So for small temperatures, magnetization at temperature minus magnetization at 0 temperature is just defined by the integral dP, and here I should write the Bose distribution function e to the epsilon p over temperature minus 1. So magnons are bosons. Magnetization, you remember that we wrote that SZn is approximately equal to S minus 1 over n sum over E1, E2, A dagger P2, AP1, e to the power I E1 minus P2 Rn, and magnetization Z is sum over n, so it's G with Bloch, S and Z. This is a uniform magnetization. So you see, if I subtract this term, take summation over n, it will give me the delta function. What I will get is just average occupation number, which then leads to this formula. And it's very easy to estimate what is this temperature dependence. How does it look like? In order to do it, I will write integral e to the power lambda p squared over temperature minus 1. So I substitute this behavior of spectrum for small p, and in order to understand temperature behavior, I need to make the integral dimensionless. In order to do it, I have to divide it by temperature to the power of 3/2, and then multiply with the temperature to the power of 3/2, which is then temperature to the power of 3/2, and here I have integral P over square root over temperature squared, dP over square root over temperature, and here e to the power lambda P over square root of temperature square minus 1. So this is how I introduce new dimensional variables. So what remains is this factor, which tells me that the behavior of magnetization is proportional to the temperature to the power of 3/2. So this is known as Bloch law. It tells us that behavior of magnetization curve for sufficiently small temperature is fully determined by excitation, magnons, and for ferromagnets it has been experimentally observed and confirmed. So then we see that here magnetization behaves as t to the power 3/2, and in the vicinity of the critical point it's Tc minus t to the power 1/2. So basically we know behavior of whole curve. What I would like to comment here is that if you ignore magnons and try to understand the behavior of curve using the simple mean field arguments based on Brilliant function, you will come, of course, to wrong result because Brilliant function difference is different from constant on a tail only exponentially. So then you will never get a power law, but only exponential deviation from the constant, which is definitely wrong. Therefore, magnons are very important for understanding the behavior of monetization curve, even for very small temperatures. Okay, if we want to calculate thermodynamics of the system, so this, say, is roughly number of magnons in the system. Like with phonons, you excite your system at finite non-zero temperature, and of course at zero temperature your system is ground state. However, for any arbitrary final temperature you have some fraction of magnum occupation number, and this is what defines the monetization. The same way, if you want to calculate the energy, which say associated with the magnons, you need to calculate the integral over dp over 2 pi to epsilon p times np. So this is np, and magnons are characterized by zero chemical potential. So estimating this integral, since epsilon p is lambda pi square, so it's pi square lambda pi square d pi over 2 pi q, and here there is a Bose distribution function lambda pi squared over temperature minus 1. So you see that in order to make this integral dimensionless, one needs to multiply it to temperature to the power of 5 because I have 5 powers of momentum in the numerator, and the remaining integral is dimensionless. So the energy associated with magnons is proportional to temperature to the power of 5 differentiating energy with respect, so n is proportional to e to the power 3 half, energy is proportional to e to the power 5 half. If we differentiate energy with respect to the temperature, we get specific heat, which is then also proportional to the temperature to the power 3 half. So this is how magnons contribute to thermodynamics for ferromagnets. Okay, as I said, magnons are spin waves. Maybe it does make sense to have some picture in mind what's going on. So, as I said, temperature. I'm not very skillful in drawing cartoons. So this is how spin wave propagates from side to side, where the rotation of the vector, and you see that everything is going on in xy plane, while in z-axis the magnetization is close to its maximum value. This is how magnons can be visualized in the ferromagnets. Okay, doing the same type of simple calculations which we already used to do for a non-ideal Bose gas, let's come for three-dimensional systems which have been summarized on this part of the blackboard to two- and one-dimensional systems. For two-dimensional system, the average number of magnons is proportional to integral p dt, and here lambda p square over temperature minus 1. So you see that this integral actually has to be analyzed separately on the lower limit, small pi, because, as well as for the gas, we suspect that some divergence can occur. So for 3D, actually, if we do the same, if we expand exponent, it's p squared dp, and here it's 1 plus lambda pi squared over temperature minus 1. So you see that integral is proportional to temperature dp. It is not divergent, temperature over lambda. So what happens in two-dimensional system if we expand exponent in the denominator and write t over lambda integral dp over p? So it's 1 over L to 1 over A, where L is a size system and A is a lattice constant. So it's t over lambda logarithm L. So number of magnons diverges logarithmically as a size of system, which actually tells us the trouble with long-range order in two-dimensional ferromagnets, and this trouble can only be resolved if temperature is equal to 0, so the logarithm is slow function, and we arrive at the statement of Merman-Wagner theorem saying that there is no long-range order for two-dimensional system when spontaneous symmetry, spontaneous continuous symmetry is broken and the interaction is short range, except for temperature equal to 0. Of course, if we analyze one dp behavior and average is proportional to integral dp, and here it's 1 plus lambda pi square over temperature minus 1. So it's temperature over lambda integral dp over t square. So it diverges as t over lambda times size of the system. And you see, even smallness of temperature cannot compensate the growing of fluctuations, and therefore the long-range order, long-range magnetic order, as well as other order for system characterized by symmetry breaking associated with breaking of continuous symmetry is impossible for any temperature. In 5 minutes we come to another manifestation of this theory, but I would like to ask you, when you discussed phonons, did you discuss the fact that the phonons in quasi-one-dimensional system lead to instability, the lattice melting, or not? Because, well, the phenomena is very similar. So the crystals, namely the long-range order, crystalline order in 1D is also problematic just because the fluctuations become so strong that the lattice melts on a large scale. But in order to do it, I hope very much that you did it with phonons. It's a nice exercise. In order to do it, one needs to calculate not the number of the average occupational phonons, but the correlated displacement, which tells you how the lattice start to melt. And you know that phonons are associated with displacements in the crystalline lattice, so your atoms move around the equilibrium position, and this is how collective modes phonons appear in the system. I think we probably need to discuss it in the exercise. It's very important. Well, when I was in university, we had a great lecturer who tried to make image what happens with a system, how this melting happens, this is like what I'm saying. You need to imagine how displacement grows and how displacement start to correlate and see that for short distances, I mean, let's take the one-dimensional chain and bend it. So for short distances, it's still okay to have the short-range order. However, the system becomes more and more fluctuating, and for long distances, this displacement, say, and this displacement become so much divergent in correlation that the system eventually breaks down. So probably I will ask Dinesh for tutorial to discuss with you this melting of one-dimensional lines due to correlations of displacements. Okay, good. Let's now come to anti-ferromagnets. Is it clear physical picture image what happens with magnons? Let's come to anti-ferromagnets. Okay, for antiferromagnets, we have linear dispersion. So epsilon p was equal to square root of 1 minus phi p squared, which resulted in sound like dispersion law. Everywhere I will take h bar is equal to 1. So this is how the dispersion looks like for ferromagnet. If we would like to visualize the picture, so we have anti-correlated spins. So there is also possibility to propagate a spin wave associated with the motion of the spin around the circle. So you see that everything is happening in xy plane, but this spin can also move like it is written here, but can move this way or can move that way. Let me probably write it this sense. So there is a coherent motion associated with that kind of propagation of wave, and there is a coherent motion with that kind of propagation of the wave. So then they tick like clocks, or then they tick in the contact. So then, in principle, in antiferromagnet, there are two Goldstone modes, unlike ferromagnet, where there is one, and this Goldstone gapless mode reflects the fact that spontaneous symmetry breaking occurs and rotational symmetry is broken. So now what do I have to change? I have to change uniform magnetization by staggered magnetization, which is a difference of magnetization of two sublattices. Then, when I speak about susceptibility, instead of speaking of susceptibility as a response to uniform magnetic field, I have to speak about response on a staggered magnetic field. Instead of Curie temperature, I have Néel temperature, and I have Néel temperature here. And let's analyze what happens with the magnetization curve. If I am interested in Nz minus M, note I need to calculate integral dp e to the power Cp over temperature minus 1. So the Bose distribution function now contains the long wave spectrum, which is sound-like. If I analyze this expression for three-dimensional case, it's p squared dp e to the power Cp over temperature minus 1. When I take it dimensionless, each power of p is proportional to temperature, therefore it's t cubed times some. So you see the deviation of staggered magnetization curve from its value at 0 temperature is not temperature to the power 3/2, but temperature 2. Just because your spectrum contains one power of momentum less, if we are about to calculate thermodynamics, so E is an integral over dp to pi cube epsilon p and p, which is integral in 3dp squared dp times Cp divided by e to the power Cp over temperature minus 1. You see that power counting of the momentum in numerator tells us that we have fourth power here, so therefore it's C temperature to the fourth, and therefore specific heat Cv, which is derivative of the energy with respect to temperature, is proportional to Tq. The same is with entropy. And this is pretty the same law which you probably discussed in thermodynamics of phonons, because what you have here is a sound-like excitation spectrum. So thermodynamics is. So when you now think about what's the contribution of different excitations to the system, you first of all need to ask the question, what is the spectrum of excitation? Because knowing spectrum of excitation, you know whole thermodynamics. And if you have phonons, which are sound, which produce sound, which is actually sound in the system, when you take a hammer and hit it, the piece of metal, what will happen is propagation of phonons in the system, which is the sound. Then you can immediately say what's the contribution to energy, entropy, and specific heat produced by this system. If you have magnons, you ask a question, what kind of magnons? Ferromagnetic or antiferromagnetic, and knowing the dispersion or character of the spectrum in the system, you can immediately answer the question on thermodynamics. For Fermi system, you remember the simple calculation told you that you can do the same kind of things, but you are in the vicinity of Fermi surface. In the vicinity of Fermi surface, spectrum of electrons and holes is linear as a function of momentum. However, this phase volume has to be replaced by Fermi momentum because we need to expand around the Fermi surface, and therefore, with the same kind of argument, with the Fermi distribution function, you will find the temperature that the energy is proportional to T squared, and this is a typical Fermi liquid dependence of the energy as a function of temperature, and therefore specific heat is linear as a function of temperature. Of course, in the course of advanced statistical physics with Professor Müller, you did calculations in order to subtract number, which is known as the Sommerfeld constant. But in order to understand the temperature dependence, one needs to make only power counting and nothing else. Okay, so now let's repeat the arguments of going to low-dimensional systems. So suppose we have 2D system and then calculate average number of antiferromagnetic magnets, which is proportional to integral P dP. And here I expand factor equals Cp over temperature minus 1. So it's temperature over C integral over dP, which is convergent. So it might give you impression that antiferromagnets, unlike ferromagnets, are stable at low temperatures for two-dimensional geometry. Actually, this is a wrong statement. So when I started convincing you that in low-dimensional systems you come to the trouble, you can see it immediately for ferromagnets, but for antiferromagnets one needs to do something more refined. Of course, the Mermin-Wagner theorem is equally applicable for antiferromagnets as to ferromagnets, and in order to see it, one needs to understand what is behavior susceptibility for systems below critical temperature. So, what was it? Both ferromagnets and antiferromagnets are characterized by isotropy of the response to parallel or perpendicular magnetic field if you are above the critical temperature. Because spin rotation symmetry is not broken, spin is rotating on the surface of sphere, and therefore the definition of what is parallel and what is perpendicular is itself not very well defined, because we don't have a direction in the system. Everything is rotational invariant. It is our choice to say that that axis is along that direction and x and y are just perpendicular to it. Unlike the system, the state in the ordered phase, where the symmetry is spontaneously broken, and therefore you have axis, preferable axis, which is an axis of magnetization. Then let's understand it for ferromagnets. So what I'm saying is T larger than Tc or Néel temperature. My arguments are equally applicable both to ferromagnets and antiferromagnets. The response function on Z field is equal to response function of X field and equal to response function of Y field. All three directions are the same. However, if temperature is smaller compared to Tc to and to N, the behavior of compensation along Z direction and X and Y direction is different. So TZZ is not equal to XX. Why? Because, as I said, the symmetry is broken. Again, to have in mind a cartoon, let's draw spin on a sphere. So if we are below critical temperature, in order to flip spin, one needs to pay finite energy, which is this Zeeman energy. Therefore, the behavior of Z susceptibility is just one of this field, one of, say, coupling constant, or it is gapped. While the behavior in xy plane, which describes as magnons, is not gapped. We have a Goldstone mode. So, this Goldstone mode appears in transverse susceptibility. Namely, I may define, instead of xy plus minus susceptibility, which is response to the field